طيب بسم الله الرحمن الرحيم. What we have today to begin with is an example. As you can see it here, it's about parallel feed MED system that has 4 effects, and it is operated by a thermo-vapor compressor TVC system. So the ejector is located there on the top of the cycle. Some information are given in written. You can see here, let me make it a little bit bigger. So we're talking about a 4 effect parallel feed. It's all MEE or MED, both are interchangeably used. MED, multi-effect desalination, MEE, multi-effect evaporation. Dash TVC, thermo vapor compressor system, is shown in the attached figure. The system operates at the following conditions. The temperature in the first effect, T1 is 58. Second effect, T2 is 54. Third effect, T3 is 50. Fourth effect, T4 is 46. So there is a 4 degrees centigrade difference between them. Whereas the steam temperature is 63 degrees centigrade. The motive steam flow rate is, which is right here, is basically 6.88 kilogram per second. The amount of vapor formed in effect number 1 is 14. This is whatever leaves effect number 1 to go into effect number 2 for heating and then joins the product line. Effect number 2 is producing 13.2 kilogram per second. Effect number 3 is producing 13.4 kilogram per second. Effect number 4 is producing 14 kilogram per second. 6.88 is going to the ejector, and the rest, which is the remainder out of the 14, is going to the condenser. And then forget about this number, which is the 52.6. This is not correct, because if you have to calculate the total productivity of the unit, actually, I'm sorry, what's being produced from effect number 4 is 8 plus 8 plus 6 is 14, yes. And whatever, if you are going to calculate 6 plus 13.2 plus 13.2 plus 14 plus 8, it will give you a number which is slightly different from this one. So this is just a typo. I got that from the book, and I just wanted to report that the collected value of the distillate is a little bit different from the value which is written here. So this is something just to remember here while we are looking at that. And the information are given here. The feed is distributed in parallel to each one of the effects. So each effect is receiving 39.45 kilogram per second, as you can see it. And the motive steam that we have borrowed here, that we have obtained from the power plant after being compressed and mixed with the entrained vapor, it is going to heat the first effect, and then this quantity is going back again to the power plant. Whereas the motive, the entrained vapor is going to join the product line again. So we have entrained 8 kilogram per second here, and this 80 kilogram per second is going again to join the quantity of the distillate. So the total distillate is this 8 plus 14 plus 13.2 plus 13 plus 6. This is the total distillate production, which will be, I guess, if I'm not mistaken, 54.4 and not 52.6. Now, what is needed in terms of calculation is the following: the plant performance ratio, the area of effect number 1, area 1, and area of the condenser, mass flow rate of the rejected cooling water. You know, the cooling water enters here. It is preheated to the feed temperature, and then part of it is returned to the sea, whereas the feed is going to be distributed equally to each one of these effects. So the quantity which is rejected is what's needed here, and the entrainment ratio, RA. So these are the values that are requested in this example. And let me see if I can be able to write here on this screen or not. So this way, this one Oh no, it seems that I'm not able to do it in this mode. This should be, yeah. Sorry, it's 55.4, I'm mistaken. So this is basically the kind of the layout for the problem. And look first at what are the parameters that are needed, because I will have to replace this screen by the other screen, which is blank, so that we can start the solution. What is needed here basically is, number one, the plant performance ratio. And let's look, the plant performance ratio, it used to be the ratio between the distillate that we are producing, which is this, and the steam which is used. Actually, in our case, it will be the motive steam, because we are borrowing the motive steam from the power plant, which means that our PR is going to be the ratio between this productivity, total productivity of the system, and the motive steam that we are using. So this is the first thing. And then I'll just talk about quickly about steps of the solution, and then we are going to go through it one by one. Second thing is talking about the area needed. To calculate the area A1, so I need to focus on effect number one, make an energy balance of effect number one. In effect number, we know the temperature, and based on this temperature, we can calculate the value of the HFG, latent heat of condensation. And we know TS, so we can calculate the latent, or we can get the latent heat of condensation for this. So the energy balance, which is given by the total mass of vapor, which is coming here, which is a combination of the motive steam flow rate and the entrained vapor flow rate, which is 14.88. This is going to enter here to condense inside. So when we multiply by latent heat of condensation, it will get us the heat transfer rate in effect number one. This heat transfer rate is used to, number one, heat the feed, which is 39.45, from T feed to T1. Remember, T feed is not given anywhere, which means that that's something that we have to calculate. So it will preheat the feed from its T feed to the saturation temperature 58, and then evaporate part of it. This part is basically D1. And this also is in balance with the area. So this is going to equal to, I'm going to write the expression of the area here as two expressions. One of them is associated with sensible heating. So the area needed to heat the feed from TF to T1. And the second, or the remainder, would be the area needed for evaporation. Why I have to write it in two parts? We discussed that earlier, that we have sensible heating. Because of sensible heating from TF to T1, then we need to calculate a log mean temperature difference. Whereas the latent part is occurring at a constant temperature. So we're going to use the expression of Q sensible is going to be equal to the overall heat transfer coefficient into the area, into the log mean temperature difference. Whereas Q latent is going to be the overall heat transfer coefficient into its specific area, into the temperature difference Ts minus T1. So this is as far as this area is concerned. And then we're going to look at the condenser. In the condenser, again, the kind of Q which is going to the condenser will be the quantity of vapor that will condense in the condenser, which is the product of the effect number 4 minus the entrained vapor. 14 minus 8 is 6. So 6 kilogram per second of vapor will condense here, multiplied by the latent heat of condensation of effect number 4, it will get us QC. And this QC is equal to the overall heat transfer coefficient in the condenser, into the area of the condenser, into the log mean temperature difference in the condenser. We are heating from tea cooling water to tea feed, and we are using vapor at a temperature of 46 as the vapor that will condense here. Then mass flow rate of the cooling water, we are going to remain with the condenser and say that Q condenser is M feed plus M cooling water multiplied by the Cp multiplied by the log mean temperature difference here, so that we can calculate the area of the condenser. Sorry, it's not the area, actually. I'm talking about the flow rate. So it should be M dot feed plus M dot cooling water into Cp into the temperature difference, which is Tf minus T cooling water. We are heating all this cooling water from T cooling water to Tf, using most of it and rejected apart, so that we can calculate how much is being rejected. Rejected brine salinity, provided that the feed salinity is 45,000. This is an energy balance for the whole plant, which is M dot feed is equal to M dot distillate plus M dot brine, and M dot feed X feed is M dot brine X brine, so that we can calculate X brine. Finally, the entrainment ratio. We are not given, for example, what is the entrained vapor pressure. We can do that, but we are going to use the equations that we have here. By definition, RA is the ratio of the flow rate of the motive steam to the entrained vapor. And we have both of them. We have the motive steam flow rate and we have the entrained vapor flow rate. So it's just a direct substitution here. So this is quickly, in a nutshell, the sort of the analysis that we need to do for this plant. Now I'm going to start going through this step by step. I already posted the header of this problem in Blackboard. So if you like to open it while I'm going through this, or if you like to follow what I'm writing here as step by step. Yeah, now let's get started. Now we're talking about a case, and there are some missing information that we should collect, like the values of the HFG. For example, HFG of steam at 63 degrees centigrade. This is supposed to be 2,350 kilojoule per kilogram HFG for effect number 1. And here I'm going to say that I'll be neglecting the effect of the boiling point elevation. There is no talk about the boiling point elevation. It's something like a fraction which is less than 1 degree centigrade. So I'm going to neglect this value and take HFG1 at the temperature T1, and this is 2,363 kilojoule per kilogram. Overall heat transfer coefficient U1 is 2.5 kilowatt per meter square centigrade, and in the condenser it is U condenser, let me get it from here, it is basically 2.036. This is a given information. Again, kilowatt per meter square centigrade. So this is the kind of information that are added to the data that should be provided in the problem. Then, when we come to the solution here, first, PR is needed, performance ratio. Performance ratio by definition, M dot distillate divided by M dot motive. This is a TVC. So whatever we are getting from the power plant is the motive steam. M dot distillate is basically D1 plus D2 plus D3 plus D4. If you remember, D1 is 14, D2 is 13.2, D3 is 13.4, and D4 is 14. So this combination divided by m dot motive steam, and the m dot motive steam for us in this example was 6.88, and that would give us a performance ratio of 7.9. So that's the first thing that was needed. The second thing needed is related to the areas. And for the areas, we'll need to calculate Q1. Q1 basically is m dot motive steam plus m dot entrained vapor. This is the amount of vapor entering into effect number 1 into HFG1. When you do this calculation, you'll find the value is 34973 kilowatts. This quantity also is needed to heat the feed. Actually, the feed I'm going to write it Fi, because F1 is equal to F2 is equal to F3 is equal to F4 into CP. Yes, يا صالح اتفضل.
دكتور in Q1 why we doesn't use a HFGS or steam?
Sorry, you are right. It's FGS. Yes, you are right. Thank you, Saleh. Into CP into T1 minus TF plus D1. Here we are going to write HFG1. Now, in this equation, what is missing? What we are going to calculate out of this equation? TF, yes. So this equation is written to calculate the value of TF. Now, Q1 is two parts. This part here is Q1 sensible, and this part here is Q1 latent. This Q1 sensible is basically the value of the overall heat transfer coefficient 1 into area 1 needed for sensible heating into delta T, which is basically T vapor entering minus current temperature of that effect, which is 58. Whereas, sorry. I made a mistake. I switched them. So this is basically Q1 sensible is U into the area into the log mean temperature difference. Sensible means that there is sensible heating. Whereas Q1 latent is U1, E1 latent into the temperature difference, which is TS minus T1. And T1 is known to us, it is given in this example as 58. The U1 is 2.5, so this one can be utilized to calculate area 1 latent, which will be, if I'm not mistaken, it should be 2624, yes. Now, log mean temperature difference is what we need now. And if I'm going to make a plot then we have vapor, which is condensing to increase the temperature. So this is T versus distance within the heat exchanger. This temperature is TS, which is the 63. And here we are heating the feed from the value that we have, this is why you obtain T feed. So from here, you obtain the value of T feed. And the T feed here, when you calculate it, you'll find that the value is 20, where did it go? TF, yeah, 45.61. degrees Celsius. So this is going to be heated from T feed to T1. So we can say that this is delta T1, this is delta T2, and then we can calculate each one of them. So actually, I'll just be consistent with the solution that I'm going to post in the Blackboard. So this is delta T1, this is delta T2, and accordingly, delta T1 is 5, delta T2 is 17.39, and then the log mean temperature difference is delta T1 minus delta T2 over ln delta T1 over delta T2, and the value is 9.94 degrees centigrade. So I'm going to take this log mean temperature difference, which is the 9.94, and then I'm going to say that this is equal to A1S that we need to calculate. 2.5 is U1, and Q1S is obtained from here. Q1S, by the way, is 1897. Whereas Q1L is basically 33067 kilowatts, of course. So from here, we can calculate area sensible, which in this case is going to be 76.33 meters square. And the area here, latent, is 2624. Now you can watch the difference between them. Actually, in that case, AS is almost 2% of the value of A latent. Will it be safe to neglect this value? This
Yes.
is 2,623, and this is just 76. Yes, I mean, it will not be a mistake to neglect it. It can be accepted, provided that you mentioned that I'm going to neglect this because I expect it to be very small. But will this be always the case? No, because it will depend on what is the value of TF, so that what is going to be the sensible heating part. Here in our case, TF is 45, which is high value. If TF is quite small, then this value is going to be significantly higher. Not much higher. I mean, I don't think it will exceed 10% of this of the total area, but I mean that we have to be careful while we are neglecting, we are assessing exactly what is the value we do neglect. So this is for the calculations of the surface area for effect number 1. Then, if we need to look at the condenser, then let me erase this. And consider the condenser. The condenser is receiving energy from whatever is coming from effect number 4 after deducting the entrained vapor. So effect number 4 is, according to this problem, is producing 14 kilogram per second. Q condenser is m dot. Actually, instead of m dot, it's probably better to put it as G4 minus m dot entrained vapor. This is what is entering into the condenser to condense there into HFG4. The value of HFG4 is basically 2392 kilojoule per kilogram. From here, we can calculate how much is the heat transfer rate within the condenser. D4 is 14, M entrained vapor is in this problem 8, so the difference between them is 6. So this difference is 6 multiplied by this value, so the Q here is 14350 kilowatts. For the condenser, there is vapor entering, which is at temperature T4. Actually, it should be T4 minus the boiling point elevation, but I said that we're neglecting the boiling point elevation here. And this is going to use to be heating the cooling water from T cooling water to TF. T cooling water is supposed to be 30 degrees centigrade. This is a part that should be given in the problem. So this is basically is going to equal to the overall heat transfer coefficient in the condenser given area of the condenser into a log mean temperature difference in the condenser. When you look at the condenser here and looking at the temperature differences, then delta T1 in the condenser is 0.39 and delta T4 is 16. TF is 45 point, we calculated it as 0.61 minus T4 actually is occurring at a temperature of 46. So the difference between them is this. 46 minus 45.61, which is this delta T1. And the delta T2 here is the 46 minus 30. That's why we have it as 16. When you calculate the overall heat transfer coefficient for the condenser, the value is 4.2. It's a small value. And having a small value, it means that we expect the surface area in the condenser to be high. So overall heat transfer coefficient in the condenser is essentially 2.036 into area of the condenser into 4.2. And from this one, area of the condenser is calculated and the value is 1673 meters square. So this is the second requirement of the problem in which we calculated the heat transfer area for effect number 1 and the heat transfer area on the condenser. We're still in the condenser to say that QC is equal m dot cooling water plus m dot feed into CP into T feed minus T cooling water. M dot feed is given in the problem. We have 4 effects, and each effect is receiving a quantity of 39.45. CP is 3.88. T feed has been calculated as 46.61, 45.61. minus T cooling water is 30 degrees centigrade. And we can use this to calculate the mass flow rate of the cooling water, which is 79.18 kilogram per second. So that was the next requirement, which is what will be the mass flow rate of the rejected cooling water. Next, we're looking at the salinity of the rejected brine. And for this one, which is basically item number 4 in the problem, in which we write the overall mass balance, m dot feed is equal to m dot brine plus m dot distillate. M dot feed is 4 into 39.45. M dot B is basically 50. Sorry, this is this is the unknown value. We don't know this value. This is the 54.4, which is the distillate quantity. From here, we get the value of m dot brine, which is 103.4 kilogram per second. Then m dot feed, x feed is m dot brine, x brine. We were given the value of x feed to be 45,000 ppm. M dot feed, here is it. And m dot brine, we calculate it from here. So the unknown here is going to be the salinity of the brine, and the salinity of brine will be calculated as 68675 ppm. So this is the fourth requirement. And finally, he's looking for the entrainment ratio, RA. You know, the entrainment ratio can be obtained either by definition or by the correlation which is given. If you remember, the correlation was like 0.296 multiplied into a pressure of PS of a certain power over P entrained on a certain power, then PM, P entrained, and correction factors. Or the defining relation of the entrainment ratio is m dot motive over m dot entrained vapor, and both of them are given. So these are given in the statement of the problem. So from here we can calculate the entrainment ratio which is needed. The problem can be extended actually to ask for many, many more things, but this is basically what was there in this problem to be asked for. You have any questions? So what I do hope to make sure that you understand this part well. The problem statement is given in the blackboard, and I'm going to post the solution. Please do not look at the solution and start solving the problem yourself without looking at the solution. If you are, and then after you finish, you can compare it. If your solution is correct, then you know that you understand how the processes are going on here. What we covered right now is basically multi-effect desalination system. Last time we solved an example of a forward feed system. Today, this is a parallel feed system, which is accompanied by an ejector or a thermovapor compressor. I can alternate the problem in a way that the m dot entrained vapor is not given, but you know the values of the pressures so that you can calculate the entrainment ratio. And the entrainment ratio basically is the ratio between m dot motive to m dot entrained vapor, so that you can calculate the entrained vapor and then continue the problem. So it's basically something that basically enough information are given and you are supposed to get the missing information. And you can formulate different problems accordingly. The important thing is that you follow the basics. What we are doing is only a combination of mass balance and energy balance for the unit.
Dr.
Now,
Muhammad,
yes, go ahead.
Assalamu alaikum, good morning.
Good morning.
One question. So when do we really account for the area of the sensible heating for the multi-effect desalination system?
I'll tell you, if you are talking about a forward feed analysis, you need to account for it for the first effect. This is important there. So the first effect in the forward feed, there is area sensible and area latent. And the rest of the effects for the forward feed, it's only latent heat. There's no sensible heat because the brine reach is saturated for each one of them. So again, forward feed, you have to account for the sensible area for the first effect only. For the parallel feed and the parallel cross feed, theoretically speaking, you should account for every one of the effects because each effect experiences sensible heating and then latent heat. But in the example that we had now, we have seen that the sensible heating part can be neglected because it's too small compared to the latent heat. The question now is, how can you know from the beginning? The answer is you cannot. So you have to calculate it to make sure of that.
And if the sensible if the area of the sensible heating of the first effect is to be neglected, then the remaining effect is going to be neglected as well, right?
Yes, for a reason, and the reason is the first effect is the one with the highest temperature, so it's going to be the highest temperature difference. And as you are moving forward to the second effect, the sensible heating will be from TF to T2. T2 is less than T1, so it's a smaller share. T3 is less than T2, so for the third effect, it will be smaller, and so on. So as you are moving from one effect to the other, the value of the sensible heating reduces.
All right, thank you.
You're welcome. Now, there is a couple of things that we need to consider. The first one of them, I don't think that all of you so far have told me what are the intended projects. And this is an issue. Some are late. Let me see here that in terms of groups, let me look at this. Let me share this file with you so that you would know what I'm talking about.
Today is the last day, Doctor, right? So anytime in today.
Yeah, anytime today should be fine. Look at this now. We have Abdullah Al-Azwari and Khalid Al-Shamrani. They are considering that analysis of two-stage humidifier water heated HDH system. And then Muhammad Al-Ghamdi and Dawood Al-Hajji are considering the analysis of two-stage humidifier air heated system. Saleh Al-Saffar and Sultan Al-Suwailim, they are considering MED system with parallel feed. Ahmed Al-Hussein and Osama Al-Shahrani are considering the analysis of MED system with forward feed. Now, these are basically 2, 4, 6, 8 persons, and we are left with 3 persons. The 3 persons left are going to work together. Now you have no option. So you are going to work together. You have project number 5, which is an MD-TVC system, or 6 or 7, or actually I have thought of another project which is going to be, let me put it here, which is again MED system with mechanical vapor compression. I'll give you the details later, but it's basically some sort of a, we have covered a single effect with mechanical vapor compression. This is going to be a multiple effect with mechanical vapor compression. So for the last group, which has the last 3 of the project, they have to select one of these 4 ideas to work on. And then again, I'm available every day at 1 o'clock in an office hour so that we can discuss it for this group or for the rest of the groups in general. So just to put things in order, then I'm going to let me see here. So that will be Abbas Al-Yahya, Hadi Al-Otaibi, and let me, where's that? So I'm going to merge it. You are not going to be all the project. You have to select only one of them. And who's the third? Who's missing?
Me, Doctor. Hussein Al Yusuf.
Oh, yes, yes. Hussein Al Yusuf. So for Abbas, Hadi, and Hussein, you need to communicate with each other today and select one of these projects. And then you have not yet started definitely, but you have to provide me with information of who will do what. And by that, what I expect today is from those who started working or those who will start working will be the following. Number one, what is the project title? A sketch of the project that you intend to work on. And if you started just in 2 lines, what you did so far, like for example, we have studied the system, we have formulated the problem, we have written the equation. I don't need the equation. I just need to see what you have done to the moment. And finally, what will be the role of everyone? So, for example, Fulan is responsible for preparing the equations, and then the other person is going to prepare it to the code, and then the first person will work on the code with him, and he will be responsible for generating the results. Then the second one is going to work on writing the report. So this kind of thing. So the role of everyone should be written, provided that the major issues should be shared. Like if you are going to write a code in ES, then I want both of you to be able to work with the code so that you can get acquainted, you would know how to write in the ES and so on. Saleh?
Yes, Doctor.
You had a question?
This was about previous question, so I don't.
It's okay, no problem. Abdullah, same thing, or you have a question?
I have a question, Doctor.
Yes, go ahead.
Doctor, I have suggestion about the role of each person. I think we are a team group. Like me and Khalid, maybe he wrote some equation and I modified the equation and I added the equation. Also about the sketch of the system. So everything is sharing.
Just write it to me. But the point is, the reason I'm asking for the role of everyone is that I do not want someone to do the work and someone just to rely on him.
I have a suggestion for that, Doctor.
And yeah, actually, I'll tell you what I'm going to do with that, which is in the last week, we are going to have like oral presentations so that everyone is going to talk about what he has done. And then I'll ask him. So if he did it, then I will know that. Okay, Doctor, but I mean, if you put like survey in the end of the project, in the blackboard, private survey, like Khalid, what will give Abdullah? Abdullah, what will give Khalid? Yeah, actually, I did that. Yeah, I did that in the previous semester, but it was okay. Like I did some sort of a peer evaluation from everyone is going to rate his peer, and this is going to be confidential. I'm going to do that, but in addition, just to make sure, ليطمئن قلبي, that's what I'm going to do. I'm going to post. I'm going to ask, like when you are presenting, I'll ask some questions for everyone so that to make sure that he fitted exactly what he has written. So that's I'm going to take care of, inshallah. So if you are sharing everything. Yes, you can say that. You can say that. Okay, thank you, Doctor. Muhammad Al-Gham, do you have a question?
Yes, Doctor. One student is enough to send the progress report through email, right?
Yes. I mean, every project is going to select a leader, and the leader is going to send me that one-page report. I'm going to a link in Blackboard so that you can submit it in.
All right. Okay. Thank you.
Fine. So what we need now to do in the last 30 minutes of the class is just to go through just introduction about the EES. So